Welcome to our latest video on chemicals from oil and the fractional distillation of crude oil. This video is suitable for GCSE students. By the end of this video lesson, you should be able to understand that crude oil is a complex mixture of hydrocarbons that was formed over millions of years from the remains of simple marine organisms. You should also be able to explain how crude oil is separated into different fractions of hydrocarbons that have similar boiling points and chain lengths using fractional distillation. And you should also be able to describe the main uses of these fractions. Coal, oil and natural gas are classed as fossil fuels. Now, fossil fuels are formed over millions of years from the remains of dead organisms. And coal is formed from dead trees and other plant material, and crude oil and gas are formed from dead marine organisms. Now, the following diagram shows how crude oil and natural gas are formed. Now, from this diagram you can see that millions of years ago dead plants and animals fell to the bottom of the sea and became buried by mud and sand, and over time the high pressure and heat from being buried turned the mud into rock, and the remains became oil and gas. Now, the oil can move upwards through the spaces in permeable rock, but it becomes trapped if it reaches impermeable rock, and therefore oil companies have to drill down through the impermeable rock to get it out, and then they're able to turn the oil into useful products in an oil refinery such as petrol and diesel. Now, in this video we're going to look at what happens in an oil refinery. And in an oil refinery, crude oil is separated into useful fractions. And crude oil is a mixture of different substances, and these substances are called hydrocarbons. And a hydrocarbon is a compound that contains hydrogen and carbon only. And in an oil refinery, crude oil is separated by a technique called fractional distillation. And the hydrocarbons that we obtain from crude oil are used as fuels, as well as to manufacture other important chemicals. So we're now going to look in a little more detail at what hydrocarbons are. So hydrocarbons are compounds that contain hydrogen and carbon only. Now, carbon is in group 4 in the periodic table, and it has an ability to bond to itself. And it does this by covalent bonding, where it's able to share electrons with another atom. Now, this ability that carbon has to bond to itself means that it's possible to have long chains of carbon atoms. So hydrocarbons can be of differing sizes. You can have very small hydrocarbon molecules, in the case of methane, CH4, which consists of one carbon atom surrounded by 4 hydrogens, or you could have much longer chains of hydrocarbon atoms, with say 20 carbons all joined together in a chain. Now, the length of a hydrocarbon chain affects its physical properties. For example, the longer the chain, the higher its boiling point, because boiling points are determined by the ability to pull molecules apart. The longer the molecule, the more likely it is to get tangled up with other molecules, and the harder it is to pull the molecules apart. So therefore, longer hydrocarbons have higher boiling points than shorter hydrocarbons. Now, methane, the simplest hydrocarbon, which just exists of 1 carbon and 4 hydrogens, is a gas at room temperature. However, if you have, say, pentane, which has 5 carbons in a chain, it is much harder to pull the molecules apart, and therefore it is a liquid at room temperature. And it's even possible to have hydrocarbons that are solids at room temperature, if their chains are very long. Now, crude oil is a mixture of hydrocarbons, and it will contain lots and lots of hydrocarbons, all of different chain lengths. So therefore, the different compounds present in crude oil will have different boiling points. And that's how we separate crude oil into its different components or fractions. We do this by using the fact that these fractions have different boiling points. Now, previously in chemistry, you would have seen a technique called distillation. And distillation is a technique we use to separate a mixture of liquids if they have different boiling points. And the following apparatus could be used to carry out a simple distillation. So in a simple distillation, our liquid mixture is heated in a round bottom flask, and in this diagram it's being heated by an electrical heater. And when you heat the mixture, the different components that it's made up of would boil at different temperatures. And when you heat up the mixture, the component with the lowest boiling point would turn to gas. The gas would rise, and as it gets further away from the heat, it cools down and condenses back into a liquid. And that's how you separate a mixture containing liquids using distillation. Now, to help the vapour turn back into a liquid, the flask is connected to a condenser, and the condenser has cold water pumped through it. Water goes in at the bottom of the condenser and out through a tube at the top of the condenser, and this keeps this part of the apparatus very cold, and it enables the vapour to cool down and condense back into a liquid. So distillation is you heating a mixture, the different components boil at different temperatures, and when a component boils, it turns to gas or vapour, the vapour rises and it cools down and condenses back into a liquid. So it involves heating, boiling, condensing, and then collecting your liquid. Now, you tend to use simple distillation if you want to separate a mixture where there's just say two components and the components have quite different boiling points. So for example, ethanol has a boiling point of 78 degrees C and water has a boiling point of 100 degrees C. So if you had an ethanol water mixture, you would use distillation to separate the two liquids, and the ethanol would boil first, it would turn to gas, it would rise away from the heat, and as it rises away from the heat, it cools down and condenses back into ethanol liquid. And the condenser would help this because it would be a very cold part of the apparatus and would mean that it condenses readily back into a liquid. Now, crude oil is a much more complicated mixture. It contains lots and lots of different components. So therefore, simple distillation would not be suitable. We need to use a different technique called fractional distillation. Now, the main difference between fractional distillation and simple distillation is the presence of this fractionating column. Now, if we are to heat up a complex mixture such as crude oil in our round bottom flask using our electrical heater, the different components will turn to vapour and rise up our fractionating column. And the component that has the lowest boiling point will turn to vapour first, and therefore it will rise up the column first, and it will get further up the column than the components that have higher boiling points, that take longer to turn to vapour, that require a higher temperature to turn to vapour. Now when the components turn to vapour, the vapour rises up the column, and as the vapour gets further away from the heat, the vapour cools down and can condense back into a liquid. Now the fractionating column helps to separate the complex mixture as it allows the vapours to cool and condense separately from each other. And this enables us to have a very efficient way of separating the mixture. Now fractional distillation is used on a large scale to separate the components of crude oil. And fractional distillation separates a mixture into different parts called fractions. And a fraction of crude oil is a mixture of chemicals in the oil which have similar boiling points. And in an oil refinery, we have tall fractionating columns with several condensers coming off at different heights. And even though the fractionating columns in an oil refinery look very different to our laboratory apparatus, the principles of how the technique works remains the same. Now this slide shows a picture of a fractionating column at an oil refinery. And in an oil refinery, crude oil is heated inside a furnace before entering the fractionating column. Now the column is hot at the bottom and cool at the top. And substances with high boiling points condense at the bottom of the fractionating column, while substances with low boiling points condense at the top of the column. So therefore, the different fractions of hydrocarbons condense out and form liquids at different points on this huge fractionating column. Now the fractions with very short hydrocarbon chains have the lowest boiling points, and they will condense out and form liquids at the top of the column, whilst the fractions with the longer hydrocarbon chains condense out and form liquids at the bottom of the fractionating column because they have higher boiling points. Now this slide shows a diagram of a fractionating column and some of the different fractions we obtain when we separate crude oil using fractional distillation. Now the different fractions include the petroleum gases, which are used for things like camping gas, and the gasoline or petrol fraction, which is used for fueling cars, the paraffin fraction, which includes kerosene, which is used as jet fuel, the fuel oil fraction, which is used for fueling tankers and ships, the bitumen fraction, which is used for tarring roads, lubricating oil fraction, diesel fraction, and the naphtha fraction, which is used to produce lots of very important chemicals for the chemical industry. Each fraction is a mixture itself of hydrocarbons with similar boiling points and similar chain lengths. So now let's recap the process of fractional distillation. So in fractional distillation, we have complex mixtures which are separated by their boiling points. And in fractional distillation, the crude oil is heated and its fractions in turn boil and become gas. And the hot gas rises, cools, and condenses. Different fractions of hydrocarbons have different boiling points, so they condense at different points up the fractionating column. And the crude oil is therefore separated into a number of fractions. Now this second picture of a fractionating column shows the relationship between the boiling points of the different fractions and the length of the hydrocarbon chains. And you can see clearly that the fractions with the highest boiling points have the longest hydrocarbon chains. So if we look at the residue fraction, which contains bitumen, which is used for road tar, that has hydrocarbon chains of more than 70 carbons. so the chains are incredibly long. Whereas if we look at, say, the gasoline fraction, which contains petrol, which is used for fueling cars, that has a hydrocarbon chain of around 5 to 10 carbons. Now the residue fraction condenses at the bottom of the fractionating column because it has higher boiling points. And the petrol fraction, the gasoline fraction, condenses much higher up the column because it has a shorter hydrocarbon chain and much lower boiling points. Now this diagram is also excellent because it shows some of the uses of the fractions in more detail. So the lubricating oil fraction contains lots of products that are used for waxes and polishes, whereas the paraffin fraction contains kerosene, which is used for jet fuel, and paraffin, which is used for lighting and heating. Now some other fractions to be aware of are the fuel oil fraction, which is used for fuels for ships, factories and central heating. The gasoline and petrol fraction, which is obviously used for petrol for fueling cars. The naphtha fraction, which is used to produce lots of chemicals for the chemical industry. And the petroleum gases fraction, which is used for fuels such as camping gas. Now, before we look at some past paper questions, it's important to reinforce some key points. So first of all, the longer the hydrocarbon chains, the harder the fraction is to boil, burn and pour. So for example, bitumen is part of the residue fraction, and the residue fraction has more than 70 carbons in the chain. Now this is going to be a lot harder to boil, burn and pour than, say, the petrol fraction, which has between 5 and 10 carbons. Now the longer the hydrocarbon chain, not only the harder it is to burn, but the less cleanly the fraction burns. So the best fuels, the ones that are easier to burn and burn the cleanest, will be the fractions that have very short chain lengths. So things like petroleum gas. Now the final point we want to make is that the longer the chain, the darker the fraction. So the first few, the petroleum gases, tend to be colourless, and the fractions in the middle tend to be more yellow, and the heavy fraction, such as the residue fraction which contains bitumen, is black in appearance. So now let's test your understanding of this topic with some practice questions. So here's our first question, and it says crude oil is a mixture of compounds known as hydrocarbons. The following apparatus is used in the laboratory to separate crude oil into fractions. Explain how this process works. And this is a 3-mark question. Pause the video, have a go at the question, and then we'll go through the answer. So now let's go through the answers to question 1. So if you said that the crude oil needs to be heated, that gets you a mark. And in your answer, if you discuss the fact that the different fractions have different boiling points, or the boiling points depend on the size of the molecule or the length of the carbon chain, that gets you a 2nd mark. And in your answer, if you talked about the different fractions cooling and then condensing back into liquids, that gets you the 3rd mark. So this is a 3-mark question, and those are the key points you needed in your answer. So here's question 2. The question is asking you to name the elements present in all hydrocarbons. It's then asking you to state what happens to the crude oil before it enters the column at point A. It also says to state what must happen in order to collect the fractions as liquids. Give the name of this process and explain why petrol is collected above diesel in the fractionating column. Pause the video, have a go at the question, and then we'll look at the second part of this question, question 2b. So here's question 2b. So the question is saying that the following graph shows how the average price of crude oil changed between 1998 and 2008. And this is in two parts. It says state the trend in oil price over this period. And then it's asking you to suggest a reason for this trend. Pause the video, have a go at the question, and then we'll go for the answers. So now let's go for the answers to question 2a. So the elements present in all hydrocarbons are carbon and hydrogen. Both are needed for the 1 mark. State what happens to the crude oil before it enters the column at point A. Well, the crude oil needs to be heated. 1 mark for that. And then it says state what must happen in order to collect the fractions as liquids. Well, they must be condensed. They must be cooled down. So they get a mark for that. And then it says give the name of this process. Well, it's called fractional distillation. 1 mark for that. And then the last part says explain why petrol is collected above diesel in the fractionating column. There's 2 marks for this. 1 mark if you said petrol consists of smaller molecules or shorter hydrocarbon chains. 1 mark for that. And this means that it has a lower boiling point. 1 mark for that. So now let's look at the answers to question 2b, part 1 and 2. So state the trend in oil price over this period. Well, it increases. 1 mark for that. And suggest a reason for this trend. Well, you could say that the crude oil is running out. It's a finite resource. And therefore that's why the price is rising. Or you could say that there's more demand for the petrol or crude oil that's causing the price to rise. So that could be because there's more cars on the road. So either would be okay for that. So now have a go at our last question, question 3. Read through the question, pause the video, have a go at it, and then we'll look at the second part of question 3. So here's the second part of question 3. So the question is first asking you to give the term used to describe the process of a vapour changing into a liquid. And then you're asked to give a reason why British oil refineries are located away from built-up areas and in coastal positions. Pause the video, have a go at the question, and then we'll go for the answers. So here are the answers to question 3. So name the fraction which contains the compound with a boiling point of -89. So if we look at our diagram, we can see that the petroleum gases have boiling points which range from -160 to 25. So -89 is in that range. So the answer is petroleum gases. And then the fraction which contains the compound with the formula C5H12 is going to be petrol, because petrol ranges from 5 to 12 carbons. And then part 2, give the number of carbon atoms in the hydrocarbon compound found in both paraffin and diesel oil. That would be 15, because paraffin is 11 to 15 carbons in the chain and diesel oil is 15 to 19. So the answer is 15. And then it says state the physical property of hydrocarbons that determine the height up the column at which each fraction is removed. That would be the boiling points. Now, if you put down the length of the hydrocarbon chains, it may be accepted. However, the length of the carbon chains determines the boiling points, and it's really the boiling points that is a physical property. So now let's look at the answers to the second part of the question. So the term used to describe the process of a vapour changing into a liquid is condensation or condensing. The reason British oil refineries are located away from built-up areas is really for a health and safety reason. It's because oil is flammable. 1 mark for that. And it says give a reason why British oil refineries are located in coastal positions. Well, the oil is imported via tankers because oil is found in the sea. It's found in the North Sea off the coast of Britain. And I probably would also accept the fact that refineries will often require a lot of steam and cooling water. So therefore, that's why they tend to be located in coastal positions. So that concludes this video lesson. So by the end of this video lesson, you should be able to understand that crude oil is a complex mixture of hydrocarbons that was formed over millions of years from the remains of simple marine organisms. You should also be able to explain how crude oil is separated into different fractions of hydrocarbons that have similar boiling points and chain lengths using fractional distillation, and you should be able to describe the main uses of these fractions. So that concludes our video. Please check out our YouTube channel, Dr. O Chemistry, and our Twitter site, which contains lots of chemistry information and links, @RadaChemistry.